If I give you a pen and ask you to illustrate time, what would you draw? You could draw a clock counting seconds or a calendar marked with days to describe it. But these images are merely physical representations of the passage of time. They only touch the surface of the mystery called time, something that controls our lives and from which there is no escape. Humans have been trying to measure time from early on through natural phenomena such as the cycles of the sun and the moon. In ancient civilizations, people knew how to use sundials to track the changing shadows and mark the movement of time during the day. Hourglasses, water clocks, and other instruments were also used to measure time before mechanical clocks were invented around the 14th century. Today, we have created atomic clocks that can measure time with incredible accuracy, with an error of just 1 second after several billion years. This allows us to define shorter periods of time than ever before, opening up possibilities for scientific research on both macro and micro scales. But the question is, what exactly are we measuring? Why is our understanding of time still so vague? From a physics perspective, time is a concept used to describe the sequence of events and the duration of their occurrence. More specifically, time is an intangible quantity used to quantify the changes in matter. In the past, everyone believed that time was an absolute concept, a continuous and independent flow, unaffected by anything in the universe. In other words, 1 second on Earth is as long as 1 second on Mars, Jupiter, or anywhere else. This seems logical because a day is always 24 hours long. There is never a day with 25 hours, or one with only 23. However, Albert Einstein's theory of relativity made the concept of time much more complex. Einstein showed the elasticity of time by combining it with space to create the concept of spacetime, something that can bend but still follows consistent and predictable laws. His theory states that time passes for everyone, but it doesn't always pass at the same rate in different situations. For example, for those moving close to the speed of light or orbiting a supermassive black hole, time can behave differently. This was proven in October 1971 by physicist Hafae Lei and astronomer Richard Keating by flying 4 cesium atomic clocks on planes around the world, first heading east and then west. The results showed that the clocks in the air lagged by 59 nanoseconds compared to the ground clocks when flying east, and they sped up by about 273 nanoseconds when flying west. This confirmed that time is not the same throughout the universe. However, a big question that Einstein's theory of relativity has yet to answer is, why can we move in any direction in space but only forward in time? If I forget my keys on my desk, I can go back and easily get them. But the time I used to do that can never be recovered. It has become the past. No matter what we do, the past stubbornly stays behind. Scientists call this the arrow of time. If one day you wake up and find yourself in an empty space, you might not be able to tell which way is up or down. But time is much simpler. You always know that it is moving forward. The arrow of time began with the Big Bang and has been moving forward ever since. We use a concept in the second law of thermodynamics to represent this, called entropy. If you haven't heard of it, entropy is a measure of disorder in the universe. The second law of thermodynamics states that systems will always become more disordered, or entropy will increase over time. The systems in our universe move from order to chaos, and this very property of the universe defines the direction of the arrow of time. Before the Big Bang, all matter in the universe was compressed into a singularity, a point so small it's hard to imagine. This is a system with extremely low entropy, or a very orderly system. It's like stuffing all your clothes into one suitcase. In that situation, you know exactly where every piece of clothing is. Since the Big Bang, all matter in the universe has expanded, making the universe a system with higher entropy. Because of entropy and the arrow of time, we have galaxies, stars, planets, and even life as it exists today. So we know that entropy is increasing, and the universe is becoming more chaotic. The question is, will time continue to flow forward forever, or will it eventually stop? To discuss this, let's consider entropy from another angle. the transition from usable energy to less useful energy. For example, fuel has more usable energy compared to its byproducts after combustion, such as heat and car exhaust. This process is happening everywhere. The light bulb in your house is converting useful electrical energy into less useful light and heat. Your body is metabolizing sugars and fats, turning them into less useful thermal energy. These processes all move in one direction, which leads us to the concept of the heat death of the universe. If entropy only increases, one hypothesis is that one day the universe will reach a state where there is no useful energy or free energy left. At that point, the universe will be filled with radiation and heat that can no longer be used for anything. The heat death of the universe is also called the Big Freeze. Nothing happens in the universe. No physical movement, no chemical reactions, and of course, no thought or consciousness. So do you think at this point, time could continue moving forward? It's not easy to give a precise answer. For now, we can only speculate. And that's not all the mysteries that time can present to us. When we study time at the quantum level, it shows us another strange phenomenon. Scientists have discovered that quantum processes can occur in reverse without violating the laws of quantum physics. For example, in quantum experiments, particles can exist in a superposition state, meaning a particle can be in multiple places or states simultaneously. This property allows events to occur without a clear direction of time, making the concept of time vague, nonlinear, and unpredictable. This makes us wonder whether time exists as a fundamental property or only as an emergent property. Emergent properties are things that don't exist in the individual parts of a system but exist in the whole system. For example, individual water molecules don't have waves, but an entire ocean does. A single thread doesn't have a pattern, but many threads together form a fabric that does. Each image in a sequence is still, but combining them in the right way gives rise to the emergent property of motion. Motion is real, but it is also an illusion. So, could time, the thing that always governs us, be just another kind of illusion? To answer the remaining questions about time, our goal is to unite quantum mechanics with Albert Einstein's general theory of relativity. This would provide a scientific link between the quantum world of atoms and the macroscopic world of stars, galaxies, and black holes in the universe. This theory is called the theory of everything, and many scientists are still working hard to research it. With this theory, we may find an explanation for how and why the universe we live in exists and even prove the existence of the multiverse. Of course, that will be our future. For now, if you enjoyed this video, please like and subscribe to the channel for more content. Thank you very much.